Hey guys, hope everybody's doing okay. What we're going to do today is continue with our equilibrium unit. We're going to do a small lesson on something called equilibrium of solutions. So we've looked at a couple equilibrium systems so far. We looked at equilibrium with vapor pressure. We had our basic equilibrium system with our reversible equations where we learned how to write the Kc expressions. We may have looked at equilibrium systems with gases and our Kp value. What we'll do today is look at something called equilibrium of solution, and it's exactly what it sounds like. You have something dissolved in water, and we're going to create a saturated solution of like maybe salt water or some other ionic compound dissolved in water. And we're going to look at the equilibrium constant and how we write that for those saturated solutions. Okay, so let's get started and take a look at how it works. The equilibrium with solutions really focuses on molarity, like a lot of our equilibrium systems, focus on. So you want to think of the molarity on the label of a bottle. Say you're doing a lab, right? And you want to use 1 molar silver nitrate, or you have, 0.5 molar barium chloride. What does that really mean? You want to think of that as the initial molarity before any dissolving happens, like the instant before any dissolving happens. So the example I have here is 0.15 molar silver nitrate. Okay? So you want to think of it as, that molarity right here is right before any dissolving occurs. I mean, silver nitrate is extremely soluble, right? All nitrates are very soluble. So it's not going to stay together as, silver nitrate ionic compound for very long at all, because it's going to dissociate because of that high solubility. Here's how you want to think of it. When you're in solution, like when these ions are actually in solution, the silver nitrate dissolves, what you truly have is 0.15 molar silver ion and 0.15 molar nitrate ion. When we learned about double replacement reactions in Chem 1, we talked about this, and we looked at this, and we actually I think we even did an example similar to this where we looked at how does silver nitrate or any ionic compound, how does it dissociate? It dissociates into 1 mole of silver, 1 mole of nitrate, and you end up with 0.15 molar silver and 0.15 molar nitrate. Back in our unit on intermolecular forces and solubility, we also did something like this with the lab simulation. Okay, so we should recognize that. So, I already went over this. A bottle labeled 0.15 molar silver nitrate really means you have 0.15 moles of silver nitrate in a liter of solution, because molarity is moles per liter. In reality, there's actually 0 silver nitrate put together, right? Because all of it has dissociated, and we're assuming all of it dissolves, okay? The bottles of silver nitrate I have to use for labs at school, there's no solid silver nitrate sitting in the bottom, right? There's no solid left. I didn't put enough in to have all of it dissolve and then have like too much and have solid left over at the bottom. I had some in there, so it dissolved and created a solution, and that's how I made it, all with relatively small concentrations. Okay, so when all is said and done here, we end up with 0 molar silver nitrate. Okay, in reality, that's what we have. And we end up with the 0.15 molar silver and the 0.15 molar nitrate. Okay? So we want to try to, this is a huge, visual, this is a huge big idea here as we progress through what we're doing today. Okay, so let's say in the lab I have a bottle that says 3.5 molar calcium chloride. Consider the following. So we want to consider what our, our equation looks like. Calcium chloride, solid, all right, dissolves, and we create calcium ion plus 2 and 2 chloride ions. That's really important here. The equation obviously has to be balanced, right? And we end up with, there's a 2 here, so there has to be 2 here. So initially, what do we have? Initially, we have 3.5 molar calcium chloride. This is before anything dissolves. So we have 0 and 0 for our initial conditions. Since the calcium chloride is going to dissolve fully, okay, it's very soluble, after dissociation, we're going to assume we're not at a saturated point here where we have some solid left over. After dissociation, we're not going to have any solid calcium chloride left. It's all in the ion form. We're going to end up with 3.5 molar calcium ion. Then what do you think our concentration of chloride is going to be? It's not going to be 3.5 molar because 1 Okay, 1 mole of calcium chloride dissociates into 1 mole of calcium ion and 2 moles of chloride. So it's a 1 to 2 ratio here between those. So our molarity of chloride should actually be 7.0. Okay? All very simple. It's all based on the molar ratio. 1 to 2 ratio, so we end up with a 1 to 2 ratio here. So time for you to try one. It's a little more difficult because we have to do something else first. We have a solution of barium acetate. All right. Now, in this previous example, I just told you it was a 3.5 molar solution. We need to remember how to find molarity, right? So this goes way back to foundational knowledge from Chem 1. You have 32.5 grams of barium acetate, and you have 750 mils of solution. So you had 32.5 grams of barium acetate. You put it in a volumetric flask, filled it up to the mark, and apparently it was 750 milliliters. So you want to figure out what's the concentration of barium acetate on the label. Okay, so what's the concentration of that solution? What's the concentration of barium acetate? And we'll go from there. Okay, so you want to think about how do we get the molarity of barium acetate. So once you get that, you can go into something like this. You can set up a chart like this in your notes. Barium acetate's formula is here, in case you forget how to write formulas. It dissociates into barium plus 2 and 2 acetate ions. Okay? What you want to do is find your initial, find your initial concentration of barium acetate. What does the label say? Remember the unit for molarity is moles per liter. Okay? So you want to figure out what's your moles of barium acetate in how many liters of solution and actually figure it out. Okay? Give you a second to do that. See if you can go through and answer the rest of these, and then we'll take it from there. All right, so you want to find out the concentration of barium acetate. So you want to figure out how many moles you have first. So we have 32.5 grams of barium acetate. Just do a simple mole conversion. Okay, 32.5 grams of barium acetate. The molar mass of barium acetate is 255.42 in a mole. And that's going to give you 0.127 moles. Okay, 0.127 moles of barium acetate. Now what you need to do is find the molarity, right? So we want to have moles per liter. So you have 0.127 moles over 0.750 liters because we have 750 milliliters, but it's always in liters to find molarity, right? So you do the math and you end up with 0.169 molar. Okay, so you have 0.169 molar barium acetate before anything dissolves. So initial concentration of the ions are 0 molar, and you have 0.169 molar for the barium acetate. All right, after it all dissociates, we're assuming all of it dissociates, our molarity here is 0. So we want to figure out what's the molarity of the barium ion, in this case, 0.169, and then what's the molarity of the acetate ion. So it's a 2 to 1 ratio here, all right? So I can't just say 0.169 because that assumes a 1 to 1 ratio. So 0.169 times 2 gives us 0.338. So 0.338 molar is what we have for the concentration of the acetate ion. Okay, makes perfect sense. We have a 1 to 2 ratio. Okay, so we should have a 1 to 2 ratio after dissociation. All right, but the bottle is just going to say 0.169 molar barium acetate. So concentration on the bottle, 0.169. Barium, 0.169. Acetate, when it dissolves, 0.338. All right, that takes care of it. So a lot of the solution equilibrium works the same way here. All right, so answers pop up. Looks like we got them right. So all of our previous examples that we just talked about assume 100% solubility, but a lot of the examples we're going to be doing going forward don't assume that. So the solution was not saturated, so all of it dissolved. Those are our previous examples. So you dissolve all of your NaCl, so you have no NaCl solid left over at the end of this reaction, and we have all ions. Notice the single arrow here. That means it goes to completion, right? And there's none of this left over at the end. Not always going to be the case though. So solution equilibrium usually involves a saturated solution, and that means we don't have all of it dissolve at the very end. So what if the solution is saturated so not all of it dissolves? We actually have an equilibrium system. So this is really, really cool because you try to envision this happening. We did a virtual lab back in Unit 2 where we could actually see this occurring. You had to make saturated solutions because part of the lab was about solubility. And when you made a saturated solution, you had some solid left over in your flask. And the simulation actually had the solids going into solution, okay? So these are red arrows here, all right? And then it also had ions in solution going back into the solid form, these black arrows here. All right, so it's really cool because at this point you have solid dissolving into ions in solution, and ions in solution turning back into solid, which is what equilibrium is. You have that equal rate of that occurring, solid into solution, and the ions in solution back into solid. So if we have a system like that where it's at equilibrium, and we have a system like that where you have a saturated solution, notice the difference in how we write that, okay? So the double arrow means the reaction is going forward, solid into ions, right? And backwards, ions into solid, right? It's doing that at the same time. So how do you write the equilibrium expression? It's super easy. It follows all of our rules from before. So our KEQ equals the concentration of Mg plus 2 times the concentration of Cl-1 squared, because we have the coefficient of 2 here. Why, where is this? Right? Where is magnesium chloride solid? Where is that in our equilibrium expression? Well, it shouldn't be there, right? Solids, okay? Solids do not show up in any K expression ever, right? This is the most common mistake, I think, with solution, like saturated solution equilibrium. All the time, students, they just don't think, and they just go into this automated mode of they do products over reactants, and that's it. They don't pay attention to small detail like the states. So don't let that be you, okay? So there is no solid in the equilibrium expression ever. It's a huge point I'm trying to make right here. And notice how it's not here in my equation, okay? So we actually changed KEQ or Kc into something called Ksp. Sp stands for solubility product. So when we're talking about solubility, right, and saturated solutions, we could call it Ksp, right? The more problems you do, the more practice, the more you'll recognize this. Ksp has the same format all the time. You will never, ever, ever, ever have a Ksp with a fraction here. You'll never have anything in the denominator because there's always only one thing on the reactant side, and that one thing on the reactant side is going to be a solid. All right? So get used to seeing this format here for Ksp. Students get confused because there's all these different, K values, right? Kc, Keq, Kp, Ksp. It's all just K. It's all just a constant, right? So don't get too hung up on it. But what comes after it as a subscript gives you a hint about what your equilibrium system looks like. So Ksp, you have something dissolving in solution. So, your turn. Write the solubility product constant, write the Ksp for a saturated aluminum sulfate solution. Okay? What you want to do is write an equation similar to this, okay? And then you can clean it up a little bit. Write an equation similar to this, and then simply write your Ksp expression that matches that. Okay? Give you a second to do it, and then we'll check it. Okay. Aluminum sulfate is Al2SO4 3, and it's saturated, so we have our double arrow. Breaks up into 2 aluminum ions and 3 sulfates. Okay, so Al2SO4 solid yields, with our equilibrium system, 2Al plus 3 SO4 minus 2. So we want to write our Ksp expression. So Ksp equals concentration of aluminum squared times the concentration of sulfate, minus 2, cubed. That's it. Okay. Notice how this is not in our answer, right? It's a solid that is never showing up in Ksp expressions. So to try to conclude this a little bit, you want to understand what the Ksp values mean. Like, what's that represent? So I know I talked about this when I introduced the equilibrium constant in general, but what would be true about the Ksp value for a solute that mostly dissolves, and for one that barely dissolves? Remember, your K expression is concentration of products over concentration of reactants. Like, definitely need to know that. And if you know math, then you're like, okay, if the product is really big, so if something mostly dissolves, the product is going to be humongous, right? So your numerator is going to be humongous. And what's the denominator going to be? If it mostly dissolves, your reactant is going to be like super tiny. So if you have a huge value in your numerator and a really small value in your denominator, the Ksp value is going to be humongous, right? Way bigger than 1, okay? If it barely dissolves, means just the opposite, right? So products over reactants. Products are really, really low, right? Because you don't have a lot of dissolving. Reactants are huge. If you have a huge denominator and a really small numerator, then you're going to have a K value that's really, really, really small. So way less than 1, okay? So that's something you want to definitely be able to recognize. College Board always gives questions where you're analyzing something about your equilibrium system, and a lot of information can be gained by looking at your Ksp value. If your Ksp value is huge, you know that it mostly dissolved. If your Ksp is really small, you know that it barely dissolved. Lots of really important information gained from understanding a really simple concept there. All right, so moving on. What's true about the solubility of these on the slide I have here? So I have a lot of substances with really, really small Ksp values. So based on what we just said on the previous slide, really small Ksp values, right, mean the substance barely dissolves. I just want to make sure I point this out, though. When I say the substance barely dissolves, that does mean that some of it actually does dissolve. All right. So if you look at these, magnesium carbonate through zinc sulfide, you may recognize from your solubility table or your solubility rules that you memorized that these are considered insoluble, right? But even though they're considered insoluble, I want you to recognize that there is a little bit of dissolving that does occur. It's an insignificant amount, though. It's so insignificant we say that it's insoluble. All right. So does a little bit of magnesium carbonate dissolve? Yeah. But when you multiply your 2 ions together, right? So your Ksp is your concentration of your products, right? Because the reactants would be a solid. Your products are really, 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 really tiny. Not a lot dissolves. So the Ksp value is really, really small. You guys can see that. As you increase your Ksp value, you're going to increase your solubility. So zinc sulfide does some dissolve, like hardly any, like the tiniest amount. I mean, look, you have to the negative 23rd power. You're talking super tiny amounts of this stuff. Magnesium carbonate, it's still a tiny bit dissolves, but the exponent tends to -5. So we've definitely more magnesium and carbonate ions floating around than we do zinc and sulfide ions here, but it's still not a lot. Okay, so to wrap up this part of the lesson before I have one final slide to go over, this kind of brings it all together here. So you have a sample of magnesium fluoride added to pure water. At saturation, the concentration of magnesium ion is 1.17 times 10 to the -3rd molar. What's the Ksp for magnesium fluoride at this temperature? So what you want to do is find Ksp. What you have to do here to start out is to write your chemical equation for magnesium fluoride dissociating, okay? And then you want to write your Ksp expression. You want to go from there. All right, I put this table here for you so you guys can try to fill that out. Very similar to some of our other examples that we did. All right, once you do that, you can try to work through some of the other parts of this. I'll try to go through it with you. If we're on Edpuzzle here, it'll pause it a couple times. We'll try to go through it semi together and semi on your own. Okay, so first thing you want to do is write your equilibrium expression. So let's take a second and do that, and then we'll go over it. Okay, so we have magnesium fluoride, so that is MgF2, solid. It's not very soluble, but it a little bit does dissolve, right? So we're going to create Mg plus 2 and 2 fluoride ions, right? So we have 2 fluoride ions over here, 2 fluoride ions, and then 2 dissociated fluoride ions over here. So what's the Ksp expression look like? Concentration of Mg plus 2, concentration of F squared. Okay. Again, MgF2 for the millionth time is not in the expression. It's a solid. Okay, don't make that mistake. So initially, like I don't even know what I had initially. Okay, I can't figure it out right now from the initial stuff in the problem. I do know I had. I should have wrote this over more. This is your initial for. Let me erase this. This is your initial for MgF2. This was the Mg plus 2, and this is the F minus 1. Okay? So I don't know how much MgF2 I started with. I do know I had none of this, because remember, initial is right before any dissolving occurs. Okay, after dissociation, I still don't really know how much I had here, okay, because I know a little bit dissolved, but I still have a ton of it left, right? Because it's not a very soluble salt. But I do know that the concentration of magnesium ion was 1.17 times 10 to the negative third. So that's 0.00117. Okay? Now I do know how to figure this out, okay? Because look, there's a 1 to 2 ratio of magnesium to fluoride. So when this dissociates, if I have 0.00117 of the magnesium ion, I'm going to have twice that for my fluoride. Okay? That's going to give me 0.00234. All right? If I go back a million slides real quick, you saw that way back here. Okay, with the, there we go, the barium acetate example, right? So we had the 0.169 barium and then the 0.338 acetate because of that 1 to 2 ratio. All right, so we're going to do the same thing here. We could actually figure out first part of our question. Okay, so what's the Ksp value? So Ksp, I had the expression here before I erased it. Ksp is concentration of magnesium, so 0.00117, times concentration of fluoride, 0.00234 squared. Okay, so 0.00117 times 0.00234 squared, and that gives me a Ksp value of, I'll put it down here, 6.41 times 10 to the negative 9th. Okay, so would you expect much of this to dissolve in water is the next question. Well, look at your value. It's extremely, extremely small. So the answer here is a big time no, right? Definitely not going to dissolve a lot in water because just look at the numbers. They're super tiny, right? Look at those super small molarities. Multiply them together, square the fluoride value, you're getting a super tiny value here. So not a lot dissolves in water at all. Last part of it. What's the maximum mass of magnesium fluoride that would dissolve in 250 mils of water at this temperature? So I want to know the amount of magnesium fluoride that would dissolve, an actual mass. Okay? So what I have to do here is take a look at what I have in this table. This is important. It's very similar to a previous example. I'm not going to scroll all the way back. But the barium acetate example, you started with 0.169 molar barium acetate. You ended with 0.169 molar barium. because the coefficients on those two were the same. Well, look what you have here. The coefficient on magnesium's ion is 1. The coefficient on magnesium fluoride is 1. So the molarity of magnesium ion will be the same as the molarity of magnesium fluoride because it's a 1-to-1 ratio. So look, you have the molarity of magnesium, it's 0.00117 molar. That has to be your initial concentration of magnesium fluoride. Okay? So let's figure it out based off of that. You know the concentration of MgF2 was 0.00117 molar. All you have to do is convert that into mass. All right? So let me redo the unit here. 0.00117 molar is 0.00117 moles per liter, right? Take a second to wrap this up. Convert that into grams, okay, of magnesium fluoride. Then convert that into, convert that into moles of magnesium fluoride because you have a 250 milliliter solution. So use your molarity calculations to get number of moles. Then convert moles into grams. Let's see what we end up with. Okay, so to knock this out, we want to multiply this by 0.250 liters. Okay, so I'm just doing molarity times volume, right? So we have our molarity is moles per liter equation, right? I want to solve for moles, so it's just molarity times my volume in liters. I'm just factor labeling it so it looks really nice. And then I want to cancel out moles. I want to go to grams. Molar mass of magnesium fluoride is, I have it written down here, 62.30 grams. 62.30 grams per mole. So the moles cancel. So you do 0.00117 times 0.250 times 62.30, and you will get your mass of magnesium fluoride. Okay, you should have 0.0182. 0.018. And actually, this 250 milliliters looks like it has 2 sig figs in it, all right, because it's 250 without a decimal, so that's what it looks like. Okay, 0.018 grams of magnesium fluoride. All right, guys, that is how you knock out a problem like this. All very manageable. It's all like small steps that add up to a larger picture here. Okay. To wrap it up, there's a little bit of homework on this, manipulating your K values. So this is something that I don't think is in your notes. You want to write this down, but it's just some shortcuts you can take. So look at some of these examples here. Here's my initial equation right here. A plus 2B yields C. And let's say I have some values, right? I have numbers, like I have molarities for all of these things, right? And my K value, my Kc, Ksp, Keq, whatever, it comes out to X, okay? I can manipulate this equation, and then it's going to ask you, like, if I manipulate this equation by doing something to it, what does my equilibrium constant end up doing? So if I take all of it and multiply by a half, okay, how does that change my K value? Well, my equilibrium constant would be this. It would be C over A times B squared. That's for my initial equation, right? I should have the brackets there, but I'm trying to save space. Now, if I multiply everything by a half, look, my coefficient becomes 1/2, this 2 becomes a 1, and the 1 becomes a 1/2, right? So I'm really multiplying every single thing by a half, which means I would, since the half is your coefficient, right, this will end up looking like this. It'll be C to the 1/2 over A to the 1/2 B to the first. Okay? What I did was I multiplied everything by a half in my expression here, like in my balanced equation, which really means I raised everything to the half power because I multiplied by a half, by a half, by a half, what you really did was you took your initial k expression, okay, and you multiplied the whole thing, like you took the whole thing to the 1/2 power. Well, instead of doing all that work, just recognize that's what you did. You multiplied everything by 1/2. So whatever your x value, like whatever your k value was here, it was x, say it was 0.02, just take 0.02 to the 1/2, or the square root of it, okay? Because something to the 1/2 power is the same as the square root of that thing. Okay, so if you multiply all of it by 1/2, all you got to do is take the square root of your k value. All right? Everything else is easy. Like if you took your initial equation and you multiplied everything by 2, well, you multiplied by 2, so you really put a coefficient of like 2 here, right? So, or if you want to think about it, you put 2 times this, 2 times this, 2 times this. So that coefficient of 2 means you're squaring it in your equilibrium expression, right? Because the coefficients end up as exponents. So if you double everything, like we did from here to here, all you got to do is square your x value. Simple. Okay? If you flip it, this is getting a little cluttered. If you flip it and you end up with c yields a plus 2b, all you have to do is inverse your k expression, right? This would look like this. It'd be a times b squared over c. Well, the initial equation was it was c over a times b squared. Okay? All you do is flip the two things. So just inverse your k expression, 1 over x. So on the homework that you guys are going to have here, you'll do it in Mastering Chemistry. Okay? It's going to give you a bunch of situations like this. It'll give you an initial equation. It'll probably give you the k value to start out with. Then it's going to manipulate it. It's going to do a bunch of different things to it. All you have to do is recognize which of these things happened and then change your k value appropriately. All right? Sig figs don't count really, so don't really worry about it. But what you want to do is, well, sig figs do count, I should say. They don't count throughout the problem. You want to wait till the very end. That's what I'm trying to get at. So if you take your answer, if you round it during the problem, you're going to get a messed up answer at the end. So what I want you to do is take your answers to way too many sig figs, okay? And just round it once when all is said and done. So don't do sig figs throughout. Just type in your calculator, type, and then whatever you get at the end, round that to proper sig figs, and you should be fine. All right? That takes care of Ksp equilibrium, and this literally, I think, is like a 10-minute homework assignment, okay? Again, use this. All right, I'll clean it up for you. Make sure you copy this down in your notes. You want to use this guide here to help you, and you should be totally fine. All right? Okay, guys, that takes care of Ksp. If you have any questions, let me know. Thanks.